Okay, let's get started here. So assignment number 1 is due at noon tomorrow. Assignment number 2, unfortunately I haven't had the opportunity to work on it. I was going to do that on Monday, but obviously plans change. So I don't know if we will have it yet for our class on Thursday to discuss. We'll see. We will finish Monte Carlo simulation and start the bootstrap today. Were there any questions before we get going?
Yes. I have a question about the assignment.
Okay.
Number 1F. We're evaluating the biasness.
Yes.
So we're given actual values for the b hat 0, 1, and then sigma hat squared, but for the variance of b hat 1, how are we supposed to evaluate if it's close or not?
The beta
Is it in the
hat 1.
notes?
For the estimated variance of beta hat 1?
Yeah.
There was, that was the fourth thing that we talked about for Monte Carlo simulation, about how you can use Monte Carlo simulation to evaluate biases. Or, let me back up. So we talked about Monte Carlo simulation in the context of 4 main things that you can use with a statistical research paper. Okay, that was the fourth one.
Okay, I'll just take another look. Okay, thanks.
Are there other questions? Yes.
Yeah, when we're just pulling out the estimates, and we need to find the estimate of the variance of beta 1 hat, are we supposed to be using something in the notes to calculate that, or is it okay just to pull it out of the summary of the?
You're supposed to, the easiest way is to pull it out of the summary.
Okay. Okay.
Summary like mod.fit.
Yeah.
Pull it out of there.
Okay, I just didn't know if that was allowed, or if
Yeah,
there was
you
more-
can.
If you wanted us to go
No,
more
no.
complicated way, okay,
No.
thanks.
Other questions?
And for part F, you only need the like how close is it? Do you need the Gaussian intervals too?
Well, you want to evaluate the unbiasedness. So what do what is needed. Okay, let's finish up this Monte Carlo simulation section here. So we were looking at the results from the simulation study that continued to find a confidence interval for sigma squared, the population variance. And we looked at basically 2 main methods, the normal base and also the asymptotic base. And then we have these 4 other bootstrap methods, which we will eventually get to in the bootstrap section. And for each of these different methods, we look at 4 different sample sizes. We also look at the data simulated from 5 different distributions. And last time we were looking at this particular plot. Make this a little smaller. Okay, so we had looked at for data that came about through a normal distribution, we saw that the estimated true confidence levels for the normal base interval were right within then the expected range if this procedure was working as we would expect. So if I had the stated confidence level is 95%, and we know that through Monte Carlo simulation that the actual estimated true confidence level can vary a little bit. And in this particular case, it was calculated to be about 0.925 to 0.975. So those are the vertical dashed lines there. And we can see obviously the normal base method is always within there for all the sample sizes. We also see with the asymptotic interval, we see this trend that as n increases, then it's getting better and better and better. And then amongst the bootstrap methods, the studentized method is the only one that's always within the expected range. Okay. Then we start talking about, well, what happens if my data is not distributed under a normal distribution? Suppose instead it is a logistic distribution. And you know, what's the difference between a logistic and a normal distribution? From stat 882. The fatter tails of the logistic distribution. So there's more area underneath the tails, but it's still symmetric. So it's a very, very similar. In fact, if I were to give you a histogram of some data distributed either normal or logistic, I bet that you couldn't really make you probably couldn't tell the difference between the two histograms, between if it was normal or logistic. Okay, because they're that similar. And so what I did was I simulated some data from a logistic distribution with exactly the same variance. I believe also I got the same mean there. I don't remember, but that's not going to matter for us because we're evaluating the variance. So exactly the same variance. And what we ended up leaving off with last time was that we saw that the normal base method is no longer working as well as we would like. For a sample size of 9, we're within the expected range, but for the other sample sizes, we're not. You know, typically, you would hope to have a statistical procedure that as n increases, the statistical procedure is getting better, but that doesn't happen here. It is happening though with the asymptotic. You know, as n is increasing, it's still getting better. And we see with the bootstrap methods, the student ties is again the best. What would be maybe the second best bootstrap method for logistic, generally speaking? So I mean, what are we looking for here? We're looking for as close to 0.95 as possible. And for those sample sizes, for let's say a sample size of 9, between the percentile, the BCA, and the basic, which is closest? BCA. And you see that trend continuing for the other sample sizes essentially as well. You also see that happen with the normal, with data distributed under a normal distribution too. Okay, take special note of that. I will tell you that for bootstrap confidence interval methods, the two best ones always, almost always, are the student ties and the BCA in terms of true confidence levels. Okay, so we can see that we're starting to have some problems with this normal base. Well, you know, it makes some sense to have some problems because after all, your data is not distributed normally anymore. And so you're violating the assumption behind it. But what's I think really concerning to me is the fact that, again, the logistic and normal distribution are not that different. Let's look at another symmetric distribution, a uniform distribution. So again, I purposely simulated data so I had exactly the same variance for the uniform as I did with the normal and also the logistic. What do you think about the normal base interval for that? Is it liberal or conservative?
Conservative.
Conservative, exactly. Yeah, I mean, look at that. Wow, that's really changed. It's sure, I like to have a conservative interval over a liberal interval, but still, I would want something that's about 0.95. And we can see similar trends with the asymptotic interval to what we did before. As n is increasing, things are getting better. Student ties interval is always within the expected range. BCA is the best of the other three bootstrap confidence intervals. Now let's change things up. Suppose now we have a skewed distribution, a gamma. Again, I selected my parameters for the gamma so that the variance was exactly the same as it was for those other three cases. What do you think about the normal base interval now? It's getting worse.
Not so good.
Yeah, I mean, as n goes to infinity, essentially, the interval is getting worse. I mean, look at that. You are down to about 0.75. Asymptotic is performing in a similar manner, although it's not as good as it had been in the other cases. But you could probably expect that as if I were to increase n beyond 100, eventually you're going to get within the expected range. Student ties interval for the first time is not doing as good as we would like, but it's not necessarily doing too bad, especially in comparison to the other ones. VCA, again, is better than the other two bootstrap intervals. And lastly, this is now actually the most skewed distribution of them all, still have exactly the same variance, and you can see again what's happening with the normal base. Now you're below 0.7 for a true confidence level. And as Z's increasing, it's getting worse and worse and worse. Student ties, do a decent job once you have a large enough sample size. Asymptotic is getting better as N is increasing as well. So, what we see here then is, a great summary of, let's see now, we had 5 distributions, we have 4 sample sizes, so essentially 20 different Monte Carlo, we had 20 sets of Monte Carlo simulation runs here. It's all being summarized by this one table, this one graph. Perhaps you can make the same kinds of judgments through looking at the table, but I think it might take a little bit longer to make those judgments. And here you can see trends that are occurring, easily as N is increasing. But you also see trends across the different distributions as well. And in fact, one thing I've thought of after I originally created this plot is that perhaps one could put the different panels of this Trellis plot, put them in order by the skewness of the distribution. And that way you can see that as the distribution is becoming more skewed, look what's happening to the normal base interval. So that's the power of using Trellis plots like this, is that it allows you to really picture what's going on and allows you to see trends. So, given that information then, if you had to choose between the normal base interval and the asymptotic interval for general practice, let's say you're teaching Stat 218 or teaching Stat 801, you probably don't talk about it in 218, maybe in 318. But 318 or 801, which would you recommend to your students? A normal base interval or an asymptotic? For general practice. Get a 50-50 shot at getting it right.
Asymptotic.
I would do asymptotic as well. Now, obviously, for even a sample size of 100, it's not always performing as well as we would like. But we have these issues with that normal base interval that even if you have a distribution that kind of looks normal, imagine if you had a sample size of 12. Are you going to be able to really feel good about making a statement that this data came from a normal distribution rather than a logistic by looking at a histogram? Probably not. So for general practice, the asymptotic would be the better one to recommend, with the caveat that you need a good sample size for this to work as you would want it to. So anyway, after I saw one, did this in one of my classes, I have decided to never ever teach that normal base interval again. How about it just in general? Which interval would you recommend? Any of them?
Student ties.
Student ties, yeah. Based upon true confidence level, you would do student ties. Of course, the problem is if you're teaching Stat 801, do you think it's going to be easy to teach the students the bootstrap? I mean, I know you haven't seen how this interval is calculated, but it might be a little bit difficult at that level for students to fully understand, well, what is this student ties interval in the context of the bootstrap? Now, how did I obtain this kind of a plot? Let's do a very simple version of this plot first. So the plot uses some functions from the lattice package. There are 2 main packages in R that do Trellis plots, the lattice and the ggplot2. I think the ggplot2 is now becoming more popular to use. There's just some stuff about ggplot2 that I do not like, and so I preferred using the lattice package. I saved all my simulation results in a file called sim_results.csv, so I just simply read it into R. And in the data set itself, this is actually shown in the notes, you have these particular variables. The confidence interval, essentially the name. I have a variable called coverage for the estimated true confidence level. We're also going to look at some expected length stuff, and then the distribution name and sample size. Now the sample size is actually a numerical value, so 9, 25, 50, and 100. Now the simplest way to do the plot is to use the function dot plot in this particular package, where in the first argument, which is simply called x, you use what's like a formula argument value, where ci corresponds to what's going to be on the y-axis, and then tilde, what's on your x-axis, the coverage level. And then if you remember in that plot that I showed you, we basically have 5 separate plots for the 5 separate distributions. And what we need to do is we need to tell what are we conditioning on. So I want to plot for normal. I want to plot for logistic. So I'm conditioning on that and then drawing the data in the plot. And so to tell R what you're actually conditioning on, you use an intuitive symbol, a vertical line, just like you would with a probability statement, probability A given B, for example. And then I'm conditioning on the distribution. My data's in set 1. I'm going to form, remember the sample sizes that I'm going to group my data essentially by sample size. I'm going to have the default legend or key drawn on the plot. Nice x-axis label. The layout corresponds to how I want the panels positioned on my plot. And this is, I don't think, very good that the authors of this package did this, but that first number there is the number of columns. The second number is the number of rows. I don't know why they flip-flop the normal way of doing that. And so if I execute then this dot plot function, this is what we get. So in case I never said this before, this is actually, each of these panels are dot plots because you're essentially plotting dots. And so you can see that this is very similar to the plot that we just had, except for we don't have the different symbol types for the different sample sizes. Also, I like to be able to control my the coloring of my my plotting symbols as well a little bit better than that. But that's a very simple version of a Trellis plot. You probably wouldn't be able to though submit this to a journal because of the same plotting symbols being used for the 4 different sample sizes. Because again, most journals still require you to be able to submit a black and white version of the plot. Yes.
Isn't it good to use different symbols because some people are colorblind?
That's another reason we use different symbols as well. Now, in order to use the different symbols and get the plot exactly like we want, unfortunately, the code's going to get a lot more complicated. I don't expect you to be an expert in doing Trellis plots with the dot plot function here, but I do expect you to at least be able to reproduce this at some point, exactly what we do here, with moderate changes to it. Okay, so one of the first things I need to do to get the plot the way I want it is I'm going to need to convert these sample sizes to essentially character values. I need to do that in order for my legend to work out right. And so to do that, in case you've never seen, yeah, I think you should have seen this before, I can use the factor function. So if I say well, let's actually just look at my sample sizes first. So you can see we have a vector of sample sizes there. And then if I were to use the factor function with it, essentially converts it to character values, or what R would call a factor. Notice it has levels there. That's how I know it's a factor. Yes?
Is there a difference between the factor and the as dot factor? I don't know if this is a tangent.
I think as dot factor will not necessarily. I'm not 100% sure.
I can look it up.
I mean, I think you're essentially trying to do the same thing.
Yeah.
I wouldn't be surprised if one maybe doesn't actually do the conversion, rather it treats it as.
Okay. Yeah.
And then what I actually want is simply the levels. those 4 different sample sizes. So you saw the levels shown here. I want to extract those, so I can simply use the levels function to extract them. I'm going to put that in an object called plot.levels. Or not, yeah, an object called plot.levels. And then now I'm going to use my .plot function again. And this still isn't going to give me exactly what I want, but I think this is a nice way to eventually get to what we want. And the code is exactly the same before, except for now I use the key argument that allows me to have finer control over my legend of my plot. And I can use simple key. The text that I want there for my symbols, that's where my plot.levels comes in. And then where do I want this plot or this legend? Let's put it on the right-hand side. And so you can see we have it over there. And then lastly, here's the more complicated version to get the exact same plot that I just had that I had drawn in the notes. Everything's exactly the same except for with my key argument, I get a lot more complicated. I put everything together in a list, and I say again I want it on the right-hand side, but I'm going to control exactly what my points look like. And to do that, I need to put everything in a list again. I want my plotting characters to be 1, 2, 3, and 4. So remember, plotting characters correspond to numbers. So 1 would be an open circle. The color of my plotting characters, black, red, blue, and dark green. The text that I want plotted, again, I have to put it in a list. My labels, there's that plot levels again. And then the panel argument, which is probably the most powerful argument that you can use in any kind of Trellis plot, not just with a dot plot here, allows you to really have fine control about what's going to be in each of those panels. So again, in terms of my plot here, I have 5 different distributions. And what we saw how everything was grouped then by distribution essentially on the plot. Each of those groups essentially are called panels in Trellis plot terminology. And what I'm going to pass in, and basically to do this panel here, I'm going to actually write a function inside my function. So this is an actual function here. And I'm going to pass in 2 bits of information, x and y, which will correspond to coverage for x, CI for y. So I pass that in there, and then I'm going to put some grid lines on my plot. I only want horizontal grid lines. So I say v equals 0 for, basically I don't want any vertical ones. And the -1 is a special way to tell R, I want my grid lines drawn at all the, oops, let me go with that. I want my grid lines drawn at all the y-axis values. Okay. Then panel.ab line, you've probably heard of the AB line function before. That allows you to draw like a line like y equal a plus b times x. Also allows you to do horizontal and vertical lines. Well, panel.ab line does exactly the same thing. Here's my vertical line at 0.95 that you saw in the previous plot. And also my vertical lines at 0.925 and 0.975 that give me the expected range. And then lastly, panel.xy plot says, well, what do I want plotted in terms of the xy coordinates? So, x argument is x, y argument is y. The coloring of the plotting points, because I know how everything's structured in my data frame itself, I know the first 6 values correspond to excuse me, my simulations for sample size of 9. I know my next ones are for sample size of 25, and so on. So that's why I'm repeating black, I'm repeating red, I'm repeating blue, and I'm repeating dark green that many times based upon what I know how everything's organized in my data frame. I do a very similar thing for the plotting character as well. So plotting character 1's plot is repeated the first 6 times. And so then lastly, when I do that plot, we get exactly what I had in the notes. It is a lot of work to do that, but that's what needs to be done to make the plot look nice. Are there any questions about that? again, think of this code essentially as a template. I don't expect you to be experts at Trellis plots here. This will be the only kind of Trellis plot I would ever ask you to do in this class. Any questions? One advantage that S+, I think, still has over R is that you could actually do one of these plots through point-and-click methods. Simply, you could drag your data, so you could actually, just like you would drag anything in Windows, you could drag your data set name onto a plotting sheet. The plot will be created for you, and then you can, like in Excel, right-click on certain things to change the various plotting attributes. Just a second. That's more than more time than I normally would like to spend on it, but I think it was needed. So of course, you would want to look at the estimated expected rates as well. And so here's the plot. Let me make this a little bit smaller. That's made it too small. Okay, yeah, that would have to do. So, now what do you think of the studentized interval?
Better larger sample size?
Yes, you see those trends with the Trellis plot. Very good. Yeah, there are some issues there with that studentized interval. I mean, it can be huge. Now, of course, if you want to be 95% confident, maybe you do need a wide interval. But when you see something like this, for example, you're at a width 150, that's something to be concerned about. And you'll see why in the Bootstrap section why that occurs. And this is the one problem that the studentized interval has. It can be extremely wide. And of all the Bootstrap intervals out there, it's usually the widest. So, because I saw that, then I thought it would be good then to do a different plot that cuts off the x-axis at about 20. And so in any kind of statistical research paper, of course, you would need to say, I cut off my axis at this value, so some of the values for the studentized interval are actually not represented. And so again, what this allows us to do is examine then the expected lengths for these. And we can see that, these intervals are, I guess, kind of in the ballpark of being the same. You notice how the normal base interval is often different from the rest. You can see that across the different distributions there. So, now based upon this, if I were to have to make a recommendation for an interval, I might be very hesitant to use the studentized interval in the very small sample size situations. And so what that kind of leaves us with is that you probably should do a confidence interval for sigma squared if you have a small sample size. And also, I might be more willing to consider using the BCA interval, for example. The BCA interval was the best of the other Bootstrap intervals, and was actually better than the asymptotic interval. Any questions? So that takes us to page 57. So while that whole discussion then was long about these simulations, I think it's very helpful as almost the ending to a Monte Carlo simulation section for a course like this, because I would expect all of you are going to do Monte Carlo simulations for your dissertation, and you need to know how to properly then summarize the results, how to properly interpret the results, and that was the purpose of this discussion. Now, I do have some additional notes here that hopefully we can go through kind of quickly through. Just from my own experience of teaching and also doing research, I felt it was good to go over these additional items that I think might be helpful. So first of all, just to make sure that you don't see this, because I know my first time that I taught Stat 950, the Bootstrap course here in 2006, my students didn't know this. to do this. And so that's why I always try to bring this up. Let's say you have a for loop and you wanted to print, or even a function itself, and if you want to print some of the results that are inside, that are being done inside the function or inside the for loop, maybe for various checking reasons, or in terms of a for loop to see how far to track your progress. What can you do? The simplest thing that you can do is to put a print statement, a print function inside the for loop or function. So if I had a for loop and I was looping over an object called r, little r, what I can do is just simply put in print r so I can measure my progress. There are ways in the R software package itself that you can actually have like a little progress window pop up that will monitor your progress as well. There's some packages that done that. Unfortunately, I don't remember what it is off the top of my head, but I've worked with a couple students who have done that in the past. So anyway, the second bullet here. Now, in your research, oftentimes what you're going to have to use is some kind of numerical iterative method to estimate some kind of parameters. Maybe it's parameters for a regression, some type of regression models, for example. And as you know, with numerical iterative methods, you might not have convergence, or some other kind of error will occur. When that happens, what that will often force R to do is abort then the for loop, or abort whatever you're doing. There's going to be, but maybe this would only occur, let's say, 1 out of 500 simulation runs. So as a way to avoid having R aborted, or R aborting the what you're doing, you can use a function called try. So imagine that you have a function that you have written called model.fit.func that fits a model with respect to some data. And there's a chance it might not work out. Well, enclose all that inside a try function. And if it doesn't work out, generally speaking, R is going to move on, let's say, maybe to the next simulated data set and try that one as well. And so that can be a very useful tool. You can also look at relative efficiency in a Monte Carlo simulation setting. We kind of talked about that a little bit. And when you do relative efficiency, what you're doing is actually comparing the estimated variances of two separate variance estimators. And so all you do is you take the ratio of the two, and then you can calculate then this estimated variance over all simulation runs, calculate the averages for both, and notice what happens, 1 over R falls out. So if, let's say, this value here was, let's say, maybe less than 1, that would say that your first variance estimator is actually better. One thing that you need to watch out for is that if you are dealing with a bias estimator to begin with, rather than looking at estimated variances, you should look at mean square errors. Why? Well, the mean square error is the variance plus the bias squared. Okay. So, for example, in an extreme case, let's say that I have an estimator, we'll call it T1, that I don't care what my data is, I'm just going to let it be value of 1. No matter what my data is. What's my estimated variance going to be? 0. Okay? And is T1 going to be a better in terms of estimated, excuse me, is T1 going to have a smaller variance than T2? Yeah, probably. Unless T2 is also another one of these nonsensical estimators. But then when you incorporate the bias, what's going to happen? Well, that mean square error for my T1 estimator is going to be inflated. Page 59, I strongly recommend that you always save some important results for every single simulation that you run. Save them in a data file. So let's say you have 500 simulated data sets, you're calculating confidence intervals for each. Save all 500 confidence intervals to a data file outside of R. There's a number of reasons to do this. One is, let's say you're doing, maybe 5 sets of simulations. So, maybe you have 5 different sample sizes you're looking at. You do 500 simulated data sets for each. Let's say during the second set of simulations, R crashes. Or for some reason your computer decides to reboot because Windows says, hey, we're going to do an update right now and we need to reboot. That's happened to my students before when they've run simulations. Well, if that happens, then you basically, if you're not saving anything outside of R, you basically have lost not just obviously the second simulation that you're doing, set of simulations, but also what happened with the first one that you had just completed. So if you're saving those results outside, you have a way to recover what you had done. Also, there will be times where you will want to actually look at every set of, let's say, results for every single simulated data sets to find maybe potential errors. And without having to redo the simulations to see that, you can go back to your data file that has saved all your results. Bottom page 59. Now, when you're performing a large simulation study, don't use your own computer. Don't tie up your own computer to do that. That's a waste of your time. Use other computers. The department has a number of student computers that are available. Use those computers. Also, the department now has a simulation computer, dedicated simulation computer. Use that one. But what's even better than those options, use the computers that are available at the Holland Computing Center. You have essentially an unlimited amount of computer power for statisticians available there. Hundreds, if not thousands, of essentially computers that are available to you to use for Monte Carlo simulation. Use those. And to be honest, I think after we talk about supercomputers here, which are the ones at the Holland Computing Center, I think you'll see that there's really no need to use the student computers in our department or the simulation computer in our department. Page 60. When I've done large simulation studies in the past, I will have my simulations going on multiple computers at the same time. If I'm not using the Holland Computing Center, or this was, I guess, more so before I was using the Holland Computing Center, I would have my simulations on many different computers at the same time. So for example, when I was doing my dissertation, I would have my simulations running on up to about 10 different computers in my department. And each of those might take anywhere from a few hours to 36 hours to complete. And so what I did was then to help organize this so that I knew when a simulation was done so that maybe I could start another set of simulations, I would have SAS or R email me to let me know that it was done. Or even you can even now, I've done this before with R, I've had it tweet to let me know it was done. Simulation studies are actually, large simulation studies, you can actually think of it as a factorial experiment. Probably taken Stat 802, so you know what factorial experiments are. Why is it a factorial experiment? Well, that simulation example that we looked at in the notes with respect to the plot, one factor was sample size. Another factor was distribution type. So essentially, you can think of Monte Carlo simulations as a factorial experiment. And I've seen this done, but not a whole lot. One can actually, let's say, design an experiment that's based upon doing Monte Carlo simulation studies. What I've seen done is people use response surface methodology so that you have a better understanding of, let's say, sample sizes between 9 and 100, what's going to happen, for example. A nice little piece of advice that my PhD major professor, we call them major professors instead of advisors at my school, that my PhD major professor had for me, a great piece of advice that I like to pass on to you, is that if you have obtained unexpected results from your Monte Carlo simulations, there's a very good chance it was actually a programming error. Go back and verify the code works correctly. A very, very good statement there. We talked about this a little bit before. so many of our statistical methods that we develop are based upon, as n goes to infinity, my method's going to get better. So why don't you try a simulation? So if you're getting unexpected results, let's say at n equal 100, why don't you try 1,000? Why don't you try 10,000? Try to get closer to infinity, because you know what should happen at infinity. So try to get closer. And if it's still not working, then most likely you have made a programming error. So let's see. And you can look at the last one on your own. Are there any questions? Yes?
So when writing the tables for your simulation results, do you, like for each loop, do you just append the results onto a single table? Do you know what I'm kind of...
Yeah, I know what you're saying. It depends upon what you're doing. You could do that. So, for example, in R, one way to append is to use the R bind function.
Mm-hmm.
Just combine what you had before with now what you have new. So that could be one potential way to do it.
Okay.
You just don't. You want to be careful not to do that. Don't do the appending too much, because let's say if you have 1,000 appends to do, that's actually inefficient.
Mm-hmm.
What would be more efficient is actually maybe to create a matrix that has 1,000 rows in it, and then to stick the stuff in there.
Yeah. Is there any way you can just write it to an output file without doing the R bind and saving the data frame or the matrix in R?
I would look at write.table, look
Yeah.
at that function to see. I
Okay.
think the default is to append,
Okay.
so you could do that.
Gotcha.
Other questions? Okay, let's move on here. So let's go to talk about the bootstrap. This is one of my more favorite topics. So I wasn't able to get all the bootstrap notes that I wanted to together in one set of notes, so there will be a second set of notes, but it'll be much, much smaller than this set of notes here. As I said in the said earlier, I taught Stat 950. I actually developed that course for our department. It was a complete semester of the bootstrap. And so what I've had to do then is take that 15 weeks worth of material, figure out, well, which do I want to include in this class in a 3 or 4 week period of time, which do I not want to include, how much detail do I want to get into this. I think I'm satisfied with what I've done here, but obviously I cannot go into as much detail. And so you can always take a look at my Stat 950 notes if you really like the bootstrap and you want to learn more about it. So whenever I talk about the bootstrap, I like to relate it back to something that you would learn in Stat 218 or Stat 801, so you can see its place in statistics. And so I first developed part of this lecture here actually for a Stat 218 class when I wasn't talking about the bootstrap, but then I use this then in my bootstrap course as well. And this is the big picture of what we do in statistics here. So on the right-hand side here, we have our population of interest, and and to relate this to a particular example, let's say that we want to estimate the mean GPA of all UNL students here on campus. And so in this big circle here, my population, you can think of, let's say, 25,000 students just kind of floating around in this blue circle with a GPA attached to them. Okay, and so my characteristic of interest then is essentially GPA, and that's going to be then my random variable. I have to put it into R statistical terms. I'm interested in a numerical summary measure of all these characteristics that these people have. That's called a parameter, specifically the population mean. And suppose we call the population mean theta to be general instead of using mu. So in general, theta could be any parameter that we're interested in, but for us it's going to be the mean. So theta is summarizing the population. Now we're interested in estimating theta, or understanding this numerical summary measure, or understanding even the characteristic of this population, these GPAs. And so in statistics, what we often do then is that we then say that GPAs have a particular probability distribution to them. So my probability density function f of y. it has a CDF of capital F of y. So what that's doing is essentially also serving as a summary of all the GPAs in that population. It shows how they are distributed. And we know from, if we know the density function, then we can come up with an expression for what theta should be. Now some shorthand notation that we're going to be using a lot. So if y is my random variable denoting GPA, I'm going to say y is distributed F. So instead of maybe writing out the actual distribution itself, I'm going to just say y is distributed F. That's my CDF that's characterizing how it's distributed. Now since this population is so big, or so difficult to get at every element, what we will usually do in statistics is that we will go inside the population and take a sample from it. And we're going to try to make sure that this is a representative sample. One way to do that is to take a random sample. That's the easiest way. And of course, with a random sample, what that essentially means is that all items in the population have an equal probability of being chosen. That's going to be a very important concept to understand for what we do with the bootstrap. Because we will also be taking random samples with the bootstrap. But again, all items have an equal probability of being chosen. So with this random sample, then, we get this smaller set of data that's a lot easier to work with, called my sample. And so in the sample itself, we have random variables, y1, y2 down to, let's say, yn, if I took a sample size of n. It has realizations of little y1, little y2, down to little yn. Those are my observed values, another way to put it. And so we're going to be interested in summarizing these observed values using a statistic. And suppose we call this statistic T, which often will be the sample mean in this particular situation. T also has an observed value of little t. So big T, of course, is a random variable. Little t is the observed value. It's just helpful to be that formal, like in the Stat 882, 883 context when we're talking about the bootstrap. Now, what I've learned about my population, my sample, I would like to extrapolate or make inferences back to my population. So what I've gotten for t here, I like to now infer then what theta should be and make that inference with a certain level of confidence associated with it. What are the two ways that we can make inferences? Confidence intervals and hypothesis tests. Each of them have a certain level of confidence associated with it. Okay, so here's my inference part. Now, how can I make that confidence statement then? I'm 95% confident, or my type 1 error rate's 5%. Not how. Why can I make that statement? What in statistics is actually driving that kind of a statement? That's what is actually highlighted in black there. What in statistics allows us to make this confidence statement?
The distribution of the statistics.
Exactly, the distribution of statistics. Everything depends upon that. So the sampling distribution, you could say, of T. And sometimes it can be easy to miss that when you're first learning about the statistical science, that everything for that inference part there depends upon understanding that sampling distribution. That's why the central limit theorem that you learned about in your first stat course, you've learned about in many courses after that, why that is so important. Because that central limit theorem gives you information about the sampling distribution of X bar, or actually other statistics as well. So then, well, what is this true sampling distribution of T? Is it normal? No, it's not. Well, In general, no, it's not, unless you have an underlying, you say your y's have a normal distribution. Instead, this is what the true sampling distribution is. Suppose I have a fixed size for my population. Let's say it's capital N. Little n is my sample size. Now there are capital N choose little n different possible samples that one could take. So for the first time, I could observe T1. Second time, I could observe T2, all the way down to let's call n choose n. Let's call that A. All the way T to TA. Okay. Now some samples are likely to have the same value for T in the end, maybe like the same sample mean. So what you could do then, or let me back up a second. So the probability then of coming up with this first sample is what? 1 over A. The probability of the second sample is 1 over A. Probability of the last sample is 1 over A as well. Now there's going to be some samples that have exactly the same value for T. And in that case, what you could do is, well, find out how many. Suppose we look at T1, for example. Suppose that there are 2 times where you get exactly the same value. How about we actually put a numerical value? Maybe it's 3. And if there was twice of all these T's, if it was twice that this happened, then the probability of getting 3 is 2 over A. And you could do that for all the possible values of T, and that would be your sampling distribution, your true sampling distribution. Well, what if, though, you had a population that had an infinite size? We often make that assumption. Well, then there's an infinite number of samples of size, and you're going to have problems doing what I just suggested that you could do. And so the true sampling distribution T cannot be characterized unless you made some underlying assumptions for the distribution of Y in the population. So what do we do in statistics then to figure out, or let's say approximate, that sampling distribution of T? Here are 3 things that we do. The first 2 you've all done in the past. So number 1, or I guess letter A, assume a particular probability distribution for the population. In other words, assume that your Y has a particular distribution F. If you do that, and you learn this in Stat 882, 883, you can probably derive a particular distribution for T. So if Y was distributed normal, and if T was your sample mean, you know that T then had exactly a normal distribution to it. We actually use this idea for the normal base interval for sigma squared. When I derived that, or I didn't derive it, I stated it. But here's the problem, and you saw this problem when we were looking at the normal base interval for sigma squared. How often can one be absolutely sure that the y's are distributed with that particular distribution F? Well, the only time that you can ever be absolutely confident that that occurs is if you're simulating the data. But we want to use then the statistical method that we have, or statistic T, to analyze real data. So that's a problem. What you're just hoping is that your statistical procedure, your inference procedure, is robust to violations of your underlying assumption. That's what you're hoping. And we saw with that normal base interval for sigma squared, it was not robust at all. So what else can we do? So B, find the asymptotic distribution for the statistic. So in other words, find square root of n times t minus theta converges in distribution to x. Now you have an idea what the sampling distribution is for t, at least for a large sample size. Okay? And that can work very, very, very well if you have if you have adequate sample size. you know, what the sample size is not necessarily the same for every single problem. So we saw, for example, with the confidence interval for sigma squared, we saw that, you know, depending upon the underlying distribution, my asymptotic interval might work better in some cases than in other cases. Also, we saw that you know, it wasn't, you know, what often maybe set 218 students like to think, n greater than or equal to 30 solves all problems. And we saw that even with a sample size of 100, the asymptotic stuff wasn't kicking in as well as we would like. So then the problems, well, how often does actually one take a sample size of infinity when you know this is going to work? Well, never. You can't take a sample size of infinity. And so then it's always of interest, well, what happens for a fixed sample size event? And that's why we need to do Monte Carlo simulations to investigate that. Also, well, how do we obtain sigma squared? Well, what that's corresponding to is this. So this x up here might be dependent upon unknown parameters, such as sigma squared. If you think of it in a central limit theorem context. You know, when you teach, for those of you who have taught this, you know, when you teach the central limit theorem, you know, you got z is equal to x bar minus mu over sigma divided by square root of n. Okay, well, what's sigma? Well, you can replace with an estimate, s, sample standard deviation, but you would expect then things are probably not going to work out as well. Oftentimes, too, we want not necessarily the distribution of t, but maybe some function of it, called h of t. How do we find that? Well, you could use, for example, if you can use a delta method approximation. What's I guess to do the whole distribution would be Cramer's theorem. Apply that, but this is based upon first-order Taylor series expansions. You know, first-order Taylor series expansion is not going to be perfect. So because of that, you might be losing some stuff. So there are some problems using the asymptotic approach. So then, and all of you have used those first two approaches to getting the sampling distribution of t. Well, what else can we do? Use the bootstrap. And that's what we will talk about for the next few weeks. So, one of the main purposes of using the bootstrap is to somehow get at the sampling distribution of t. If we have the sampling distribution of t, then we have a way to do statistical inference with a certain level of confidence associated with it. So, about the bootstrap. It's all dependent upon basically one thing, and that is, remember in that part A above, for getting at the distribution of t, we had to say y was distributed f. We had to state the actual distribution. So you might be thinking to yourselves, well, okay, I don't know what f is. Could I maybe replace it with f hat? That's all the bootstrap does. It basically tries to do what we just saw in part A, but replaces f with f hat. This is what's called the plug-in principle. So instead of having f, we plug in f hat. Well, what is f hat? Well, from what we learned earlier in this course, we could use the EDF. That would be one possible value of f hat, and that results in what's called the non-parametric bootstrap. That's what we mostly focus on here. But what you could also do is use a parametric distribution for f hat. So let's say, for example, you could use this, a normal distribution with the estimated mean, in other words, a sample mean, and from your observed data, and also then the sample variance from your observed data. So you are plugging in estimates for the parameters. This still is making the underlying assumption that y is distributed normal, but of course you don't know what mu is. You don't know what sigma squared is. So by plugging in then their estimates, you're doing what's called a parametric bootstrap. And parametric bootstrap can actually be quite useful. So now once we have then this sampling distribution, well, what can we do with it? Well, as you might expect based upon my introduction, well, that's when confidence intervals and hypothesis tests come in. But you can also use it maybe for some other purposes, such as, you've looked at set 883, how to estimate a bias. Well, we can do the same thing with the bootstrap without knowing what the true parameter is that you're trying to estimate. That's the cool aspect of it. Also, you can use it to estimate a variance as well. So let's talk about then the history of the bootstrap. Where did it come from? Because I think it's important to know this. And I guess it's been in the more recent past. So anybody heard of someone by the name of Bradley Efron? Okay, he's one of the biggest names in statistics, and he's a professor at Stanford right now. I think he's in his 70s right now. He's the one that's usually credited with developing the idea, but others had come up with aspects of it prior to that. But he kind of synthesized it, put it together, and what really started the revolution of using the bootstrap as his third method of getting at a sampling distribution. This happened in the late 1970s when he did this. If you ever go to JSM, I recommend that you attend a talk by Efron because he's a very good speaker, and usually every year he's there. But back in for JSM 2007, he didn't go because he was busy doing something else. He was at the White House getting the National Medal of Science from, at the time, President Bush. I've never seen an actual video of the presentation. I would have loved to hear President Bush's introduction, talking about that, maybe that resampling thing, or that bootstrap thing, I should say. But I never have heard, I've never seen the actual video of the presentation. I've never actually met Efron myself, but I've attended a number of his talks. And interestingly, the first talk that I ever attended of his was actually here at the University of Nebraska. He was here as part of, and if you can believe this, a Bayesian conference hosted by the university back about 1998. At the time, it was actually put on by the stat people in the math department. And he was the keynote speaker for that conference. And I, at the time, was a student at Kansas State, so I drove up here for the 2-day conference. Okay. So, well, where did the name bootstrap come from? I mean, this is one of the few times in statistics where we actually have a interesting name for something. And there's kind of an interesting story behind it. And it actually comes from the fact that what we're doing with this bootstrap, basically the plug-in principle, some people might refer to this as almost data abuse. So to help understand that, with that parametric bootstrap that we looked at, notice all I did was I replaced the sample mean for the population mean in it. I replaced the sample variance for the population variance in it. You might be thinking, well, wait a second, I want to do inference here. How can I just simply do that little substitution and think everything's just fine with it? I should, that part A introduction there, I need to know what the actual true distribution is for F. And so I'm maybe using my data beyond what I should normally use. Also, with the non-parametric bootstrap, what we're going to actually be doing is a lot of random samples. Not from the population, but from our actual original sample itself. These are called resamples. And so some people, when this, this idea came out, thought, well, wait a second. How can you take a sample from a sample? That doesn't make sense. And so that then drove was John Tukey, who did like the bootstrap, to come up with the name the bootstrap. And it's based upon the classic book, The Adventures of Barn Munchausen. Anybody read that book? I've never read it myself. But it's a classic book. It's actually, it's old enough now that it's in the public domain, so you can Google it and get the book for free. And this is a story, and this Baron guy was how should I put it? He could do remarkable things through his imagination, I guess you could say. And in one part of the book, he was actually stuck at the bottom of a lake. So imagine, I'm the Baron. I'm standing on the lake bed here, and I'm looking up, and I can see, the water above me. I don't know. Maybe I have some kind of oxygen tank with me so I can breathe. But anyway, he was stuck at the bottom of the lake, and he was like, okay, how do I get myself out of this situation? And so what he did is he reaches down to his boots and he pulls himself up by his bootstraps. And that's how he pulls himself out of the lake. I don't know, I guess he could have swam, but but anyway, that's how he got himself out of the lake. And we know you can't do that. And that's essentially what Tukey was thinking when he named this procedure the bootstrap. That to generate more data, in other words, the resampling that you do with a non-parametric bootstrap, to generate more data like that from your original data set is kind of like the same thing what the Baron did, in terms of you can't pull yourself up like that and get out of the lake. And so that's how the name came about. There was actually a 1989 movie based upon the book. Unfortunately, the Baron didn't pull himself out by his bootstraps. Instead, he had a ponytail, and he pulled himself out of the lake by pulling up on his ponytail. I think it's, and I don't know German. I believe that the book was written in German. I think it's due to maybe different understandings of the translation of the German to English, perhaps. And so there's the Baron. And there's the Baron pulling himself out of the lake by pulling up on his ponytail. I recommend don't watching the movie. It's really not that great. Okay? If you want to read the book, there's some links. And here's a little excerpt from Efron's 1979 Annals of Statistics paper, one of the places where he introduced the world to the bootstrap. And we will focus on this part of the acknowledgments. Okay, so Efron says, I wish to thank the many friends who suggested names more colorful than the bootstrap, including Swiss Army knife, meat axe, swan dive, jackrabbit, and my personal favorite, the shotgun, which, to paraphrase Tukey, can blow the head off any problem if the statistician can stand the resulting mess. Again, you don't typically see this in the statistical world. I guess the creativeness in a non-statistical context for naming and other stuff like this. So that's why I think it's kind of an interesting story about it. Now, now let me back up a second. So, the 1980s then, the hot research topic was the bootstrap. One of the hot research topics. And there was lots and lots of research done to prove that indeed it worked, even though it might seem, what you're doing you shouldn't be able to do. And this research extended over into a little bit in the 1990s as well. But pretty much most of the research in the bootstrap itself, the core principles of it has been done. And most in the research that's left, there's some that sometimes occurs, like the Annals of Statistics and stuff like that, that really gets into some of the mathematical stuff behind the bootstrap. But where the bootstrap now is most useful, I think, for students who are doing a dissertation, is that the bootstrap provides you a way to solve a problem, getting at that sampling distribution of T. Let's say you don't want to use asymptotics to get at a sampling distribution of T. Or maybe you don't want to make this underlying assumption that Y is distributed normal. The bootstrap gives you another option to solve your problem. Because for most of you in a dissertation setting, you're going to need to know what a distribution is for a statistic. The bootstrap provides almost an automated way to do that for you. And so that's why I think it can be every student should know about the bootstrap. and this is how it's most often used in research nowadays. For example, for my own PhD research, basically I had a non-standard problem where I needed to figure out what the distribution is for some statistic. Let's call it T. Then I know that asymptotically that my distribution converged to the sum of I equal 1 to, well, we'll call it C, of lambda I and some chi-square 1 random variables. I know I could prove that. Where the lambda i's were some eigenvalues of a covariance matrix. Well, the problem was is that estimating this distribution, the lambdas were dependent upon parameters, didn't necessarily result in a good estimate. And so that's why I ended up using the bootstrap then to estimate the sampling distribution for T instead. Now, it's not just well, it took a while for statisticians to, let's say, use this kind of as an everyday thing to use in practice. The reason was because imagine again in the 1980s, you needed to do this bootstrap procedure, which basically relies on Monte Carlo simulation, and you have to do it a lot of times. They didn't have the computing power in the 1980s, so I would imagine, although I was quite young then, back in 1979, I would imagine when this first came out, when statisticians first read that paper, they probably thought, no one's ever going to use this. I can't do, R equal, let's say, let's say 4,999 simulations, at a drop of a hat. I can't do that. But starting in the 1990s, obviously computing power has always gotten better, but especially in the 1990s, we were still starting to get to a place where people can do this, and it's not going to be that difficult. Also, in '93, Brad Efron and one of his former students, Tip Sharani, in 1993 wrote a book called An Introduction to the Bootstrap. This made the ideas behind the bootstrap accessible. As I said, Efron's a good speaker. He's also a very good writer, too. Then in '97, Davison and Hinckley wrote a book. And this is actually the book that I used for my Set 950 class. It's better than the Efron and Tip Sharani book, although it is a much harder read. And what was really cool about both those books, they also provided a set of S+ functions to automate this process of using the bootstrap in a statistical software package. Before then, it wasn't done. So they made it easy for people to use. And so this then, where nowadays, not just statisticians, but non-statisticians use the bootstrap on a daily basis, let's say, to do stuff. And so anyway, so that gives you a little bit of history behind it. The S+ functions for Davison and Hinckley's books have been translated into R, and those are the functions that we will use for our class here to do the bootstrap. Before those functions came out, someone would laugh at you if you were going to use a statistical software package to do the bootstrap. They would have expected to use Fortran or C++. In fact, when I actually first sat in on a bootstrap course in 1996, offered by my advisor, and he told all the students in that class, you're going to have to use C++ or Fortran to do this stuff. Some students don't want to take the easy way, and they try to use Davison and Hinckley's S+ functions. The problem was that they ended up crashing our computer system because all of them were trying to use that, and doing stuff in a statistical software package takes a lot longer than language like C++ or Fortran. So anyway, let's see. So I think that's a good place to stop. Are there any questions? Okay, that's it for today.